طيب شباب, we are continuing with the gain margin and phase margin. I thought we will I will give you an example where we will be talking about, okay, how do we use the concept of gain margin and phase margin in the stability of the system. Okay, so what we are giving in here in this system, we have the body plot, the magnitude plot. This is magnitude, and this is the phase. And we would like to determine
The gain margin and phase margin.
Yes, I spent quite some time in this morning, but unfortunately, when I save it, seems to me I didn't save them. You know, it is better presentation, but anyway. Okay, so the first thing, okay, we would like to obtain the gain margin, phase margin. In order to obtain the phase margin and gain margin, we have to obtain the gain crossover frequency, which is the point or the frequency at which the magnitude equal to 0 dB. Okay. We will also determine the phase crossover frequency, which is correspond to the minus 180 degree in the phase. So suppose, let me start by determining the,
the gain margin.
Gain margin. Okay. If I want to determine the gain margin, then let me go to this point in here, minus 180 to the phase, and go and find the intersection.
Which is the phase crossover frequency.
Okay. So now I can read from this line what is the what's the magnitude of this phase crossover frequency. At the same time, okay, if they don't ask me, I don't have to find it. I can go directly, take a line, and intersect this line with the with the magnitude and read from here.
Yes.
Okay. Then the gain margin is going to be whatever this value. Okay. So let's say whatever, let's say minus 8 or minus 10. Okay. Then the gain margin equal to 0 minus 8, and it's going to be 8.
Yes.
So the gain margin will be positive if we are below the 0 dB.
That means we are in a stable region.
In the stable region, yes.
Yes, because the minus 180 will be killed, because if it has a positive dB, now we are unstable.
Okay, now let me find the phase margin. In the phase margin, I will go to the 0 dB line. This is the 0 dB line, and find this intersection. Okay, I'll go straight down and read the phase. Let's say the phase equal to 140, minus 140. The phase equal to minus 140.
No. Yeah, I don't think so, Doctor. I don't think so. Because
no,
minus 9.
Less, even, okay. Let's say minus 80, or this is 90, it's 80. Minus 80.
Then you subtract it from minus 180.
So the phase margin equal 180 minus
80.
Minus the 80.
Yes, or minus 80 minus of
okay.
minus of my hand. Yes.
Or minus 180 minus. But what I'm trying to say, this is the positive direction of the phase margin. Anything, okay, above the 180 degree is considered positive. Anything beyond the 180 degree will be negative.
دكتور.
Yes.
ليش 180?
Okay, just 1 second.
And 180 is corresponding to
look, the 180 and the 0 dB are important, because look, to have this G of S. Okay, this is Y and this is R. So what is the transfer function? Y of S over
1 over G of S 1 over بس G of S.
G of S over 1 plus G of S, which is basically the characteristic equation is going to be 1 plus G of S, characteristic equation, F of S, which is equal to 0. Okay?
Okay. Yes.
Okay, now rewrite this one as G of S equal minus 1. So what's the
No,
magnitude?
I see it.
The magnitude
Magnitude 0.
1, and the phase will be the minus 180 degree or 180 degree.
هذا دكتور for unstable.
No, this point, I mean, the question is why we take the 0 dB and the 180, because this is correspond to the, you know, they are correspond to, you have a poles on the J omega axis, or
Yes.
they are correspond to in the Nyquist. Okay, this is the Nyquist. This is the minus 1. Those are correspond to the minus 1 in the Nyquist. So all of them, they are part of the characteristic equation, but we are representing them differently. Okay, in the root locus, okay, we use the stability related to the J omega axis crossing. Nyquist is this one, and the body plot is the 0 dB and the 100 degree.
دكتور معلش بس عندي سؤال.
تفضل.
الفيز دايجرام هل دائما يوصل للماينس 180 ولا مو دائما يوصل لها؟
الفيز دايجرام؟
ايه يعني لو كان عندنا فيرست ديجري مثلا 1 اوفر جي اوميجا بس ولا 1 اوفر اس بلس 1
Yes.
هل حتوصل للماينس 180؟
لا ما راح توصل. It depends. Remember, suppose you have G of S equal, let's say G of J omega equal to 1 over, okay, or J omega, let's say plus 1. And here I will have J omega, then J omega over 5 plus 1. And let's say I have a complex, okay. I have a complex J omega, let's say plus 10, okay. And suppose this is square. What will be the final angle? What do you think?
The contribution of each one.
Okay, each pole will contribute 90 degree. So 90, 180, and I have 2 in here. That will be 50, but I have a 0 also. So ultimately, the final angle is going to be minus 270. But
لا كيف عرفت يا دكتور معلش كيف؟
كيف عرفت كيف؟ Remember, عبد الرحمن, I gave you the body plot with the final angle equal to 90 multiplied by difference of between poles and zeros.
جميل.
Okay, I think I mentioned this before. So because look, at infinity, if omega go to infinity, what's the contribution of the what we have in here? What will be the angle?
احنا قلنا 270 ولا؟
90 is going to be, isn't it?
If just for the upper ear.
Yeah, and then this is 90, this is 90, and this is 180 because I have 2 poles.
Yes, you're right.
ايه دكتور
Yes.
سؤالي اذا
كيف؟
ايوه في سؤالي اذا السيستم ما حيوصل لماينس 180 كيف حنسوي الاستابيليتي بالمارجنز؟
Oh, good question. I thought I'm coming to it. Okay. What you are saying, suppose I have a system, okay. Let's have a system G of J omega equal, let's say, K over J omega plus over 2 plus 1. Suppose you have this system. صح ولا لا? That's what you are saying.
Yes.
Okay, tell me, what is the gain margin in this case?
Gain margin. No.
As you said, you never reach the 180. It means the gain margin is infinity. This is the, again, if you go to the Nyquist, we have similar thing. Okay, remember we have something like this. And this is the -1. If you increase K, you will go in this direction. You'll never, okay, you will never reach the -1, which means that the gain margin, the system is always stable for all K. And the gain margin in this case equal to infinity. Okay, or your question is very valid, valid question, excellent question. Yes, in certain system, the gain margin, you know, sometimes the system is unstable, sometimes the gain margin is 0, I cannot add, and sometimes this, the gain margin will be infinity. It's possible. If you don't
I
intersect,
see, Doctor.
okay, if you don't intersect with 180, so this, okay, again, to this system which you have, so basically the phase is going to be like this. This is 90, minus 90. Okay, so it never intersect the 180. Okay, which means that, you know, okay, the frequency is going to be at infinity, which means that, you know, my system is going to be, you know, stable all the time.
تمام واحد دكتور يعطيك العافية.
Allah يعافيك. Okay, now, why the gain margin, if the gain margin here is negative, sorry, the gain margin is positive, but the gain, if the gain is negative, why the system is stable?
Again, Doctor, again the question.
The question is, if I am here,
Why the system is stable?
exactly.
Yeah, because it's a minus gain. That means the minus 180 is killed. It's
Okay,
not.
no, think about it, Abdurrahman, think about it, because we study the stability in Nyquist a lot. Think about what does this correspond to? Okay, this is correspond to, okay, if let's suppose the gain is here minus 10. So basically minus 10 equal 20 log of the magnitude.
صحيح مظبوط 100%.
Okay, now, so I have minus what? Minus half.
الباور minus يعني 1 over root 10. G 1 over root 10.
G, okay, so this is going to be, or let's, okay, to make it easier, make 20. That's,
طيب يعني 1 over 10.
so 1 over 10, so it's going to be, okay, 1 over 10, or this is going to be, yes, I mean, this is going to be minus 1, which is going to be log the magnitude, and the magnitude then G is going to be, the magnitude of G is going to be 0.1. And if you relate it to the Nyquist, this is the minus 1, and this is 0.1. So if we are below the 0 dB, we are in this area. Okay, and we will not encircle the minus 1.
يا سلام يا سلام. Yeah, now it's clear. يا سلام.
However, if you go in the positive, we will be somewhere in here. And we will be encircling the minus 1.
طيب دكتور معلش انت you mention a case I lost you while you are mentioning such a case that even if you increase K to infinity the system will be also stable.
Yes.
Which case?
Okay. Take a case. This is minus 1. this could be K over J omega, let's say, plus 1. Take J omega. Okay. Take this case.
Mm-hmm.
What is the point? What is this point? What's the magnitude of this point?
Magnitude of this point, it is
K.
K, right? Right.
K.
At
Now,
omega
K.
0 يعني.
Okay. Yeah, because omega equal to 0. So this is K.
صح.
This is K. Where do you go?
Again.
This is K.
Mm-hmm.
K equal to 5. Suppose if K equal to 1, this is the point. If K equal to 10, you will move in this direction.
Oh, yes, yes. So you will just increase in the right. Yeah.
Okay, which you will never encircle the -1. And the system become, okay, always stable, okay. And we said the gain margin will be infinity.
Oh, and this is desirable, of course.
But you know, I mean, this is special systems. I mean,
Yeah, this cannot happen in reality in
Yeah.
any case.
no, maybe no. There are certain systems, no. Well, okay. Let's, you know. Okay. We said the phase did we cover the phase margin as well?
Yes, you said that we go to the gain crossover and then we find
Okay.
the difference
So
between the angle.
okay, the phase margin. Okay, we come to the 0 dB intersection, go down and read this angle, and subtract from 180, and that will be the system. In this case, the system becomes stable. Now, here we have a situation where this is the magnitude curve and this is the phase curve. Let's, you know, take the find gain margin. I need the gain margin. So to find the gain margin, I will come to the 180 degree. The first thing, find the intersection of the phase with the minus 180 degree. So this is the intersection. Read the frequency. This is the crossover frequency. Okay. Omega phase. Then go up and intersect with the magnitude curve. So if you go in here, this is basically what you are going to have. Okay. Then gain margin equal the intersection point from point magnitude of point 2 or step 2, okay, minus 0, and that will be your gain margin. And in this case, look, it is above the 0, so the gain margin is negative, and the system is stable. Sorry, in this case, we'll take, okay, so it's going to be the 0 minus this quantity, 0 minus. So as I said, okay, what's important to understand, if you are above the 0 dB line, then the gain margin is negative. Now for the phase margin, you go to the 0 dB, take a line, intersect, and go down, and read the phase. The phase is going to be beyond the 180 degree, and the system become unstable.
دكتور
ايوه
المثال اللي فات الجين مارجن ما كنا نبغاه نيجاتيف.
كيف؟
قلنا احنا في المثال اللي فات انه الجين مارجن نبغاه يكون نيجاتيف.
The gain margin. This is another example. Okay. The other example we have the gain margin is positive. الحقيقة ما فهمت سؤالك.
هو هي 0 minus the intersection ولا intersection minus 0؟
Look, either way you take it, what I'm saying, if the gain margin is above the 0 dB, the system is, the gain margin will be negative and the system is unstable. Anyway, you want.
Because that means we are circling -1.
Yes, exactly. So if it is above the 0 dB, the system is unstable. If you are, below the 180 degree, the system again become unstable.
Can we, Doctor, think of it from the perspective of e to the power, the magnitude? Because if it's negative, it will decay. If it is positive, it will grow exponentially.
Well, this is okay. Definitely, there are many things you can do, but the easiest thing which we have, as I said, if you relate it to the either the j omega x's or the Nyquist, it will be simpler. Now, is clear? Majid, who asked me, Majid or?
يس دكتور رابع، بس كنت ملخبط شوي.
Okay. Now, let's move. Let's take another example. Suppose I have this system, a unity feedback system, and I need the gain margin and phase margin at 2 gain, at 10 and at 100. Okay. Why do you think we need to increase the gain sometimes?
Because we have to account for the loss in the input.
Any other thoughts?
Reduce the steady state error.
Exactly. Reduce the steady state error. Reduce the steady state error. Abdurrahman, you said what?
To account for the loss in the input. And
There's
also
no loss. Okay, you define it. No, it is steady state error. Okay.
اتوقع برضه دكتور شو اسمه settling time. You decrease the settling time with increasing K.
No. Look, K, we study K. K related directly to the steady state errors. Okay. So suppose we'll come to it later. But suppose now for K equal to 10, this is the body plot. This is the magnitude and this is the phase. So let me get the gain margin. In order for me to get the gain margin, I will go to the -180 degree. Okay, and intersect and go up. Read this area. This is my gain margin. So in body plot is much simpler than the Nyquist. But already you are putting a time in doing the plot. Okay, and this is the gain margin. For the phase margin, okay, let me take the 0 dB line and intersect it with the graph, with the magnitude curve, and go down. Read the intersection of the phase curve with what we have. Read it. And then see how much difference from the 180 degree. And that will be your phase margin. Any question here?
يس دكتور، هل ممكن واحدة منهم بس تتحقق والثانية لا؟
هل واحدة منهم تتحقق كيف؟ ممكن واحد يكون yes، واحد يكون positive والثاني يكون negative قصدك.
إيه.
There is a possibility. If you remember, I have said, I gave why it is not enough to take only the gain margin, because look, suppose we said I have this curve and I have another curve. Okay, and this is the -1. Okay, so I have two curves. Both of them, they have same gain margin. Okay, because this is, you know,
حتى الفيز هنا يا دكتور بوزيتيف is not negative الفيز.
phase is going to be different. But
This is not negative, it's positive.
it is positive, but look.
Because it cannot be negative the phase margin. Why is that?
It could be,
Because
no, look, it could be, no, look. It is that why, you know, I mean, if you have this situation, when you implement, okay, I mean, physically, yes, I mean, mathematically, yes. But when you implement in the system, possibly some of the parameter will bring you in here, even though you did your calculation based on this one.
لا انا قصدي دكتور انه ما ادري فهمت سؤال ماجد صح ولا لا، بس قصدي انه هل ممكن يكون الجين مارجن بوزيتيف والفيز مارجن نيجاتيف or vice
There is a
versa?
possibility. I think there is, or
That means there is inconsistency between.
Or at least, look, or at least it's going to be like this.
But in this case, it will be both of them will be negative.
No. If you take no, I'm saying if you are not including, you are still in here in this point. It means that your system is very badly, you know.
This is not a system, maybe.
Yeah, it will be very badly conditioned.
I see.
Okay. Now, so yes, in general, we need both of them to be positive. Now let's take, we increase K. K is 100. Okay. K is 100. So let me again come to the 180 degree and go up. Remember, okay, this is the 0 dB line. So I'm above the 0 dB line. And my gain margin become -12. For this system, if I want to find the phase margin, this is 0 dB, go down. Okay. And you will be crossing the 180 degree. You are beyond the 180 degree. Okay. Any question here?
دكتور الان ممتاز، يعني كذا الحين فكره هذا بيفيدنا في الديزاين.
تجينا بالديزاين. Yes.
يعني this is will be very helpful in design in choosing selecting the parameters. Okay. And
That's correct. Okay. Let's move.
دكتور
Yes.
مفترض اذا بغينا نختار قيمه اوكي تكون من الروت لوكس.
كيف؟
بغينا نعرف اذا الكي بيخلي السيستم انستيبل ولا لا، مو مفترض نشوفها من الروت لوكس احسن.
We are looking for, Madri, if I understand you correctly, maybe I missed something. Okay.
لا وقال الدكتور روت لوكس احنا usually we have investigated the k, the parameter k or the gain using the root locus, but the root locus will not give you يعني how much gain you can add to give
No,
the.
of course, no, of course. What are you talking about? Of course. Okay. Let's take this situation. This is the root locus, let's say. So we evaluate this, okay? This frequency, what will be the K? So K will be from, you go from 0 until I reach this point.
اصلا احنا اصلا we vary the k to plot the root locus.
To infinity.
Yeah, we vary the k to plot the root locus, so it will give us.
Exactly. But no, what I'm saying, in this situation, there is a possibility that the system become unstable for certain K.
بس دكتور هو ايش قاعد يقول ماجد؟
ماجد وجدت المشكله ايه بالصوت ماجد يعني جزاك الله خير عبد الرحمن لان بصراحه ماجد
فكرته جيده، يقول انه الروت لوكس اسهل بكثير من احنا نروح شو اسمه البودي بلوت، بما انه الروت لوكس يعطينا كل
الديزاين
كيز.
معظم الاحيان الديزاين الديزاين we will be using both root locus and the body plot. So it depends. Look, it depends on the situation, depend on the application. It is I mean.
يعني هو ايش الفكره يا دكتور؟ what his point is the body plot is for a given k, but the root locus is for the whole for k from 0 to infinity. You know what I mean? So to
yes,
to
for
investigate,
a given,
investigate.
yeah, but yes, but you can vary k. Okay, you can. Okay, for example, in the design, okay, what do you want to do? You would like to operate your system in certain particular k. So first of all, suppose you have steady state error. Okay, you satisfy the steady state error. Okay, and that will give you the required k. Okay, then
Usually, doctor, in the real life, also BM and GM is also a specification that you have to satisfy because the system might be exposed to certain instability. So we need.
But if you just wait, hold on, let's hold on.
Yes.
In a few slides, I will show you يعني where
شكلنا قاعدين نستبق الأحداث.
شكلكم كده. But anyway, I mean, there are two alternative way of doing it. Okay, let's now go to the final topic of the course. So in the next few lectures, we will be focusing on the design. Remember the roadmap which we put at the beginning of the course. We said we started with the modeling. We discussed the Laplace transform, we discussed transfer function, we model physical system, we put the state space representation, the signal flow graph, and other things. So all of those, we did in the modeling. Then
Yes.
we went to the analysis. Okay. In the analysis, we study the behavior of the system. Is the system stable, unstable? In the time domain, is the response good, bad, need improvement, and so on. Okay. Now,
This is Dr. Asraha amazing catch up. And now you summarize everything in the course in this slide.
I'm trying. ربنا يسهل. Okay. So suppose a system, after you do the analysis, your system become unstable. What do you do?
You have to consider
Okay.
investigate this.
So we would like to work with a stable system because unstable systems are not useful. But we have to, stabilize them. Or you are doing second order system, you want the speed of the response is faster. So what do?
You decrease the settling time. Yani.
You go to the design. In the design, we are going to limit ourselves to the body plot, root locus, and of course PID will be part of both the body and the root locus. It doesn't mean there is no other method of design. No, there are many methods. If you go to the state space, then you will use what we call state feedback. Okay, to design. But in here, since we'll be limiting ourselves to
سؤال دكتور.
method of design. Okay.
Question دكتور.
تفضل.
بالنسبة للcontrollers, we always hear that the BID, proportional integral derivative controller, is the most commonly used controller in industry.
Yes.
Do we have now in research, or I don't know if certain companies are applying certain controllers that are advanced, يعني not BID, but let's say an advanced version of a controller, better than BID. Do we have such?
If you go to Aramco, you see the plant حقهم يعني it is well, very advanced controller. Yeah.
Not BID.
Yeah, not well. I mean, PID could be, but if you are talking about take the network of the kingdom and the electric, I'm talking about the electric network, okay? How many controllers you will have in there? Because you know what you want a localized control, you want globalized control. So the control, no, definitely there are, you know, Honeywell, and in here we have in Dahlan Techno Valley, Yokogawa, they are very, they are specialized in building controllers. So controller, no, definitely it's beyond the, inshallah, Allah Ta'ala, like, either Hina, well, if you go to Aramco, those who will go to Aramco, or any other plant, you will see that the controller, there are many, and the research, there is a lot of research in many areas of the control, or building controller. Okay, now, what we want to do in here, we will be talking about, you know, okay, the compensation, and then we'll talk about lead compensator, phase lag compensator. The lead lag, I have my doubt if we will, you know, we will mention what is it, but I don't think, because the time we have only about what, 6 lectures. How many lectures we left with? About 6, I think. Okay, so I don't think we'll be touching. We will be also talking about the PID controller. Now, again, why we are doing compensation? We said, well, okay, you do compensator because, you know, I mean, you would like to, you know, rectify certain situation. Because sometimes, you know, okay, we need a compensator because sometimes we can live without compensator, but sometimes no, it is not possible. Well, the example for that one, suppose, okay, you have the root locus. Again, let me use the same plot. Okay. And this is here. Okay, suppose you have, this is the root locus. And suppose I need, you know, certain specification to have certain zeta such that the dominant pole in this point, okay, by varying k, remember, then root locus, k is the parameter which we are changing. Do you think I can reach this point? I have,
Why not?
this is k, g of s. Okay, and the specification given to me, I would like to satisfy the roots are in here.
Yes, underdamped. Yes.
Okay, so it is possible by adjusting K and reaching here.
Usually increasing K أصلا will drive the system to underdamped case.
Well, but anyway, no. Okay, let's be specific. I want to go to this point. I can, because it is on the locus. But suppose the point in here.
Oh no, you cannot here.
This is definitely, changing K will not help. I have to insert a compensator. I have to put a compensator.
A compensator. What do you mean, Doctor, by compensator?
Oh, okay, controller. We are coming, just hold on. So the compensator basically, okay, roughly speaking, if I have a system, this is one of them, this is G. I'll put another system in cascade. Okay, such that it will adjust, okay. When I said the example in here, okay, this is the original plot. If I want something in here, I'm adding, I can add poles and 0 so that I will force the system. I will force my system to go, let's say, in here by adding, you know, another system. Okay. So the compensator, basically you are adding another device, okay, which will adjust the behavior of the system, and it will give you the desired performance which you want. Okay. Well, the devices, of course, and here we, you know, at the first stage, we design mathematically, but later on in the physical system, the physical the physical compensator or the controller will be electrical system, mechanical, hydraulic, and so on. And that's what we will implement. Well, look, the performance of the system, because you want to design, so you would like to, have certain performance. What are the performance of the system which we have studied so far? In the time domain, let's talk about time domain. What are our, parameters which we want?
Performance, you mean overdamped and critically damped?
Exactly. No, we mean the overshoot, how much overshoot I need in the system, how much, what is the speed of the response, and the speed of response will be in terms of the time rise and settling time, steady state error. So all of those are things which we want to satisfy. Okay. You want your system to behave in such a way that it will give you the desired thing which you want from your system. This is the time domain. What about the frequency domain? What do you think? In the frequency domain, there are two types of parameters. For the open loop system, we talk about the gain margin, phase margin, and the crossover frequencies. Of course, remember, we have shown that the phase margin is related to the zeta, which is related. So the phase margin, we said, zeta equal 0.001 of the phase margin. So they are related. In here, remember, we talked about the bandwidth, we talked about the resonant frequency, we talked about the peak, MP. And again, those also are related. The bandwidth, for example, related to what in the time domain?
The time domain, the bandwidth,
Yes, the
settling
bandwidth.
time.
The what?
Settling time, maybe.
Settling time or time rise? No, the speed of the response.
Yeah, the speed, of course, because if the bandwidth is higher, the time will be less.
Exactly. So look, in order to do the design, we will be using different, type of requirement, and we would like our system to satisfy the desired requirement. This is, just to point out, the exam, the final is going to be on May 5th at 1 p.m. I will be talking about it later. Okay.
معظم اختباراتنا دكتور 1 PM. عجيب
انت الحين رمضان.
طيب حطوها في الليل 10 PM طيب.
في مجموعه بس انت ما يمديك يعني انت تعرف how many لان تعرف what 10 days you want to give the exam for everybody. No, the exam, now currently, some of the lectures in the after the graduate courses, they shift them from 5 to they start at 9 and they finish at midnight.
يا لحاله قتل.
Okay. Now the design philosophy. Okay, suppose I have the system and I need steady state error for a ramp input not to exceed 0.01. Okay. So what is the value of K which will satisfy this condition? This is a unity feedback system. R, A, and Y, and this is G. So is steady state or the error equal to what?
Error is the R of S. Yes, multiply by the 1 plus over 1 plus G of S, yes.
Okay.
This is type 1, so we can find KV.
This is type 1. So that's why I'm going for the ramp, for the good point. Not because look, if it is step, since this is type 1, so the error is going to be 0 and we will be satisfying the error. We are not looking for that one. What will happen if I have my input is run, which it makes more sense.
Yes, if it is, I think, Doctor, if it is unit step function, the error will be 0.
Yes, and it's satisfied, so OK will do it. So I'm interested in no. Suppose I have a run. So if this is the case, then the E steady state equal limit as S goes to 0 of S E of
S
is equal limit S goes to 0 of S times 1 over 1 plus K S 1 plus S and 1 plus 0.0125 S.
هذه يرجعنا يا دكتور لشابتر steady state error.
Exactly. 1 over S square because the run. And this is equal to?
This is less than or equal to 0.01.
Okay. Yes. So let me put the S inside. If S multiplied by the 1 and S goes to 0, this will be 0. Then the S in here, cancel this S, and I will have the steady state
1 over K.
1 over, yeah, this is 0, sorry, 1 over K.
Yes.
And this should be less than 0.01. Which means,
يعني K أكبر من 100.
okay, so this is great. If I want to eliminate the steady state error, okay, basically,
not to eliminate,
K
just
greater
not to
than
exceed.
100. Okay.
Not to entirely eliminate the steady state error, but there will be less than 0.0.
Yes. But the problem,
the system might go to the underdamped and another response, of course.
The system become, you can go and check the system. The system become unstable at K equal to 81. Okay, so we fix one problem, we create another one.
Which is more dangerous.
Okay, no, both of them are important. So what we want to do in the design, look, what we have in here. I have two plots, one with small value of K. And the Nyquist, even though, look, we're not going to use Nyquist, but Nyquist is good for demonstration. So this is my Nyquist plot. So the system is stable, but it's not satisfying the steady state error. While if I increase the steady state error to 100, okay, I eliminate the steady state error, but I will go in this curve. And the system becomes unstable. The design philosophy is, how can I start with this one, okay, and then as I move, I'll try to switch to the other one. Okay, so this is the net result. I use the benefit of the low frequencies. Look at K, at steady state error, it means that I'm at low frequencies. Okay, so I'm satisfying them. And at the same time, I will build a controller such that I will be in this region. And my system is going to be stable. By using one compensator, which will do the job for me. Any question?
الله يعطيك العافية دكتور.
I think we're stopping here.
Doctor, I have a question.
تفضل.
You said the compensator, its job is to meet the requirements outside the default
Yes.
control design.
Okay.
But what's the catch if we can use the compensator? Like, what's the disadvantage of using a compensator in our design?
Well, first of all, you pay more money.
Yes, of course.
Of course. Okay. I think this is the disadvantage. Disadvantage حقك انت you are making your systems more complicated, but beyond that, no, there is no disadvantage. As I said, the compromise in here in the design, as I said, the compromise which we have shown in here, that if I increase only one component, okay, which can be done. For example, when I satisfy steady state error, if you have the system in here, okay, we could satisfy the steady state error without any without adding a compensator. However, by going to the 100 or beyond the 80, my system become unstable. That's why I need the compensator. So the compensator in general, no, the system become more complicated. It need more analysis, but beyond that, no, there is nothing. There is no disadvantage.
تمام دكتور الله يعطيك العافية.
الله يخليك.
دكتور الكمبنسيتر هي نفس الكمبنسيتر اللي درسناها في الفلترز في الاوزيليترز.
Yes. We will come. Look, next lecture, inshallah. Unfortunately, this lecture we couldn't make it. Next lecture, inshallah, we'll go more detail in.
يعطيك العافيه دكتور.
حياك الله.